In this section, we'll take a look at linear and angular velocity, and actually I want to first describe the difference between the two. So linear velocity is the speed at which something travels in a straight line. So if you look at the diagram that I have here, linear velocity is tangent to the circle. And so at this point along the circle, right here, the point is traveling at a particular speed. It's linear velocity. And angular velocity, which is omega, and omega is this Greek letter, is the speed at which something rotates. So the closest example you probably have that you'd be familiar with would be RPM, rotations per minute. And so the angular velocity multiplied by the radius gives us the linear velocity. And in order to think about why the radius is relevant in this case, imagine if you can, and maybe if you used to be a skater when you were younger, maybe you still are. I know we used to play a game where one person stood as the anchor. They would be the center of the circle. And you would join arms or hold a rope. And they would have a person here like this. The person here is the anchor. And then maybe someone else is out here. And I've drawn them separated just so that you can see. But maybe they're actually holding on, or you have a whole bunch of people together. And this person starts to skate around in a circle. Okay. So this person also then follows suit. We'll do them in red. All right. So we're all going around in a circle together. What do you remember, if you've ever done something like this, about the speed at which these two people were traveling? They're going around a circle at the same rate. They're coming back to this point at the same time, right? That means their angular velocity is the same. But look at how far the outer one is traveling compared to the inner one in red. The outer one is traveling a lot further, and therefore it must be going faster. And that would be so V for the outer person is faster than V for the inner, right? He's whipping around much faster than the one on the inside. So the radius, which is here, this distance, is relevant. The further out you are, the faster you have to travel to get back around to the same point. And that's the difference between the linear velocity and the angular velocity. So the distance from the center, which is the radius, makes the difference on how fast the person has to travel around to get back within the same amount of time. Notice the radius for the inner one is much smaller than the radius for the outer person. Okay, so we have the relationship that linear velocity is equal to angular velocity multiplied by the radius. And another important factor is that angular velocity must be in radians per unit time right here. So this is radians per time. Any time is fine, but it must be radians per unit time. So theta has to be in radians. And often this information doesn't come to us in radians per time. It comes to us in rotations per minute. So we have to convert a rotations per minute into a radians per minute. The standard SI unit for angular velocity is radians per second. We will use various ones, but just so you know, this is a standard. So since angular velocity will often be given to you in a revolutions per minute or rotations per minute, RPM, it's important to be able to convert that into radians per minute. And we need to know that one rotation or one revolution is equal to 2 pi radians. So for every revolution that we make 2 pi radians. So therefore, for 120 revolutions, we must multiply by 2 pi times 2 pi, and this will be per minute. Still, I'm not changing the time yet. That will put it into radians per minute. So this will be equal to 240 pi radians per minute. And if you want to see what that is as a decimal, let's multiply 240 times pi, which is 750, I'm going to round up, 754 radians per minute. Next, we will actually change our 120 revolutions per minute into radians per second. We already know that this converted to 754 radians per 1 minute, and I would like to make that into seconds. So 1 minute is 60 seconds. So in order to do that, we want to then do our division 754, because this is going to cancel minutes, and put it into radians per second. And so 754 over 60 radians per second. And that number is 754 divided by 60 gives us 12.6 radians per second. Okay, now let's take a look at an example where we will calculate the linear velocity of the tip of a fan blade. So imagine a fan, like a ceiling fan, and so we have the circular motion like this, and we have a blade that goes like this on our ceiling fan, right? The tip of the fan blade is here. This is the tip, and it is rotating with a linear velocity of something we want to figure out. And that linear velocity is equal to the angular velocity multiplied by the radius. And the angular velocity must be radians per time. So what do we know about this? We know that the fan blade is 1.5 meters, the radius, 1.5 meters, that's our radius. We know that it rotates at 200 rotations per minute. So that is an angular velocity, 200 rotations per minute. For each one of those rotations, it travels 2 pi radians. So we want to take our 200 and multiply by 2 pi to get it into radians per minute, which will be 400 pi radians per minute. And if I want to see that as a decimal, 400 times pi, which is 1257, let's use as a rounded value, rads per minute. All right, now the linear velocity is, now I can use my omega, which is in radians per minute, 1257 rads per minute, and multiply that by the radius, which is 1.5 meters. And I will get it into, so 1257 times 1.5 is, we'll say 1885.5 meters per minute. Okay, so our unit that we use is the linear measurement per time. The radians end up just kind of canceling right out. All right, that's your examples for linear and angular velocity.